Okay, yeah. So homeworks are on me. I think I more or less passed everyone. But if I failed and you have questions, just go for me. Okay. So in comments, general observations. The last three problems were kind of an issue for most of you, but hopefully it's gonna get better. Now, Niels has asked me to ask you guys to just go on the conversation on Canvas about the workshop. Do you want it tomorrow or do you want it in the following week? Disclaimer, I might not be the following week. I don't know if that counts. If it doesn't and you don't care, just go on the discussion and write I'm indifferent, which is I don't care in a nice way, okay? Because Niels is apparently getting pressured to entertain discussions on Canvas. So just please do that in the break. Just write, I don't mind, anything works. If you don't care and if you have a preference, just type it in there. Other than that, yeah, I think that kind of goes for everything. Any questions up to this point? Cool. Now, we're going to start the last part of integrals, which is substitution. And this is a rather tricky one. Why is it tricky? Well, because I can't give you more or less a blueprint of when to apply it. I can show you how to apply it, but it's sometimes hard depending on the problem, and even for me, to know when to apply it. And I'll explain it in a second. Also, disclaimer, for those of you that have been to the workshop and done the problems at the, not the workshop, the seminar for this week. Disclaimer, but I will do this. There was a problem where you weren't taking the primitive, we were doing by parts, but you weren't taking the primitive of the exponential. You were thinking of x. And I was thinking, guys, can you hear me? Yeah, I think you should. Okay, I was thinking, you know, I told you always apply it to the exponential, and in the homework you have to apply it to x. So kind of confusing for you guys. Which one should I choose? And the answer for that is in the homework, you're given like the special conditions. So it's not a blueprint of how to solve it. But I guess I'll elaborate on this since I got a lot of questions about this. I'll probably just make a video explaining to you guys. Also, I do get a lot of emails, and I think some questions are really, really good. So, and I think most of you might have them, but not ask them. So what I'm probably going to do is just keep emailing me questions. And I might just do like a short video asking them anonymously, of course, and everyone can just see the questions, maybe clarification, maybe help some people. I don't know. I'm just thinking, do you guys think that might be useful? Just me answering like questions from other people online. Obviously, you won't know who asked them, And yeah, so just keep emailing me questions. But now let's get back to work since I have to do a lot of stuff today. So substitution, right? It's basically, you know, we were used to, and we're doing substitution, and we're going to do the first part in the indefinite integral, okay? Don't worry, just like the by parts, the definite is more or less the same. But in the indefinite integral, the idea is that I have to compute something, an integral of an f of x dx, right? This is what I have to compute. And I don't know how to compute it. So the idea is maybe I can just swap this x, okay? Maybe I can just replace it. That's where substitution comes into play, right? Like I'm just gonna compute an integral, an f of y, okay? This is like the first step you gotta think of. Now, obviously, I cannot have dx there, right? Because I have y here. So the formula, what you're gonna apply is the following, and I'll give you the blueprint. So first of all is choose a variable / function to replace. Okay. Then, and I'll do an example immediately after. Then just choose a variable to replace. Let's just say u is equal to f of x. Okay. Let's just say that. Let's just say I had an f of x computation and I replaced it with a u. Okay. And then instead of computing the integral that I had, which was, let's say, integral of g f of x dx, I'm just going to compute integral of g u du, okay, where du, this du thing, this notation more or less, is just equal to f prime of x dx, okay? Don't worry, this is just the formal definition. We're gonna do an example. It's gonna be pretty clear, and it's the hard part of my parts is not necessarily the substitution is not necessarily the formula itself or the application. It's when to apply it. That's kind of what is going to be tricky, but the application itself is rather simple. Let's take an example right now. Okay, let's just compute integral x square root of x plus 1 dx. Okay, any ideas how to solve this? Maybe by parts, I don't know. Regardless, we're going to do it by substitution. What's the idea here? Let's just say I want u to be x plus 1. Okay, this is what I want to replace. Usually, when you have a square root of a function, not really nice to work with, kind of hard actually. You won't be able to solve it. So that's why this is why the idea comes into place. Let's just say this x plus 1 here is just my u. Okay, so let's take it step by step. What does x become here? This x is just u minus 1. Okay, and now the final thing I have to replace is this dx. Okay, so you have the formula that dx multiplied by u derivative, which is just again x plus 1, has to be equal to du. Okay, so dx multiplied by x plus 1 derivative is equal to du. What is x plus 1 derivative of x? It's just 1. So this is just equal to dx multiplied by 1 equals du. So they're equal. Okay. So why did I do all this thingies here? Because I can replace this integral with, and let's take it slow. I said x is u minus 1. It's u minus 1. Okay. Multiplied by what do I have here? Well, x plus 1 is u, so this is just square root of u. And I said dx is equal to du from here, so it's just du. Everyone follow me on this? Okay. So again, what did I do here? I have something inside the integral, inside the square root. Usually a bad sign, can't really solve that, or it gets really ugly really fast if you make something wrong. So what I did is I thought, okay, let's just replace what's inside the square root with a variable. Let's just denote that with a u. Okay. And after that, I expressed all my integral in terms of u. Okay. So if u is x plus 1, then x is just u minus 1. So here we go. X becomes u minus 1. X plus 1 becomes u by notation. And dx is equal to du. Okay. Any questions here? Yeah. Yeah, because, yeah, of course, because by notation, I said, I want to get rid of square root of something ugly. It's better. So I just denote x plus 1 with u here. Okay. I just choose x plus 1 to be u. Could I have chosen square root of x plus 1 to be u? Yes, it's completely your choice. What variable you choose to denote by what. Okay. Now, the sad part is that it's your choice, but not all choices are correct. Like not all notations are going to lead you to the solution. And unfortunately, I cannot say always take that one because there's no such thing. Otherwise, math would be simple, right? But in this case, what I can tell you is when you have square root of something, usually assigned to, get rid of it. Okay, cool. But let's come back to where I am right now. I'm stuck here. Okay. Why did I do all this thing if I still have here? Well, this is just equal to integral, and I break the parentheses here, u square root of u minus u du. Okay, which is just integral, and I split it right now. u 3/2 du minus integral of u du. And we know the formulas for this, right? Like they're in the book. If you don't know them, they're in the book. I'm just gonna write it straightforward. Yes, apologies for that. Completely correct. Sorry about that. So yeah, I distributed this thing in the parentheses, and I have u squared of u, and then just square root of u. So sorry about that. Yeah, correct. Completely correct. Okay. Regardless, we do know the formulas for this. It's just u to a power of something, and they're in the book. Taught them in the first lecture. If you still don't remember them, it's just, let's see if I remember it by heart. Now let's write it. I think let's write it here if I remember it. It's integral of x to the r dx is just equal to 1 r plus 1 multiplied by x r plus 1 plus a constant. Right, this was the formula, I think. I'm really bad with memorizing them. That's why I just kind of compute them every time, okay? But this is the formula. When you take derivative of the right side, you get the left side. So I just apply it here, and I get 1 over, again, just applying it, 3 over 2 plus 1 multiplied by x 3 over 2 plus 1. Oh, no, this is u, okay? U plus minus, it's a minus here, sorry about that. Minus 1, again, now I'm computing the other integral, okay? So this integral, this is a minus 1, same thing, a half plus 1 multiplied by u, a half plus 1, plus a constant in the end. Okay, I didn't copy the constant for each of them, I just put it at the end, doesn't matter. Okay, so this is a result, okay? Now, careful here. Just follow me with this computation, and then I'll show you something. Okay, any questions up to what I did at this point? Okay, so careful now. This is what I had to compute, right? In x, in apples, but my answer is in oranges, okay? It's in u. So once you get to the formula, you have to replace u with your initial x. Does that make sense? Okay, so I started here. Let's write it. I started integral of x square root of x plus 1 dx. This is where I started, and my result is 1 over 3/2 plus 1 multiplied by u 3/2 plus 1. Just copying the result of what I got there, okay? 1/2 plus 1 minus u 1/2 plus 1 plus a constant. Okay, this is where I started. This is where I got. Do not leave the answer like this. As I said, you have x on the left side, u on the right side. Apples, oranges, they don't mix. Technically they do, but scratch that. You know, you get what I'm saying. Two different things. So just plug it back in. U is equal to x plus 1. So what do you just do here? You just replace here, okay? So I just replace. And I get replace back. So integral of x square root of x plus 1 dx is equal to 1 3/2 plus 1. I had u here, so it's just x plus 1 3/2 plus 1 minus 1/2 plus 1 x plus 1 again, because it was a u here, 1/2 plus 1 plus a constant. Okay, and now you're done. Okay. Yeah. Any questions from the start, if you guys want? Anywhere outside. Otherwise, we're just gonna take another example, and hopefully it becomes clear. Let's see what example I can give you that. Okay, I like this one. Cool. So any questions on this? Otherwise, I'm just gonna do another example. Okay, so I'll do another example. Let's just say I'll give you like a pseudo rule. Again, do not quote me on this, but it is helpful. This is your thing, okay? This is what you have to compute. Do you want me to write it with X or is T fine? That's basically the same thing as this one. Okay. So I have to compute this integral. Another kind of rule in quotation mark, is fractions bad. Fractions, limit of fractions when using L'Hopital, good, because you can apply L'Hopital. Computing integrals of fractions, not good, okay? Especially ugly fractions. So the idea is to replace the ugly fraction underneath with something that's easier. So this is where the idea comes into play. Let's just say u is equal to 1 plus t squared. Okay? Good. Now, what you want to compute always is the du dt kind of thing. So let's just see. As I said, it's dt multiplied by u derivative is equal to du. Okay? Just like we did last time, literally the same steps. I'm following them right now. So it's dt multiplied by derivative, derivative of 1 plus t squared, derivative of t, okay? It's equal to du. So this is just equal to dt multiplied by 2t multiplied by 2, okay, whatever, is equal to du. Everyone follow me on that? Just did my replacement, and now I'm trying to get rid of this dt. Again, when you do the substitution, as I told you, this d thing tells you who you're integrate over. So you cannot replace a u inside here, but keep the same dt. You got to replace dt into d of u. Okay, this is why I'm doing this. Okay, so I got this thing. Let's see what I can do. So this is just equal to this is where by parts a little bit becomes a little bit icky, because I cannot replace. Remember, in the first example, I just had dt equals du, so I just replaced them. At this point, I need to have dt multiplied by 2t in order to get du. Okay. So how do I get that? Well, can I just write something like integral? This is just integral of t squared, 1 plus t squared, multiplied by t, d of t. Okay, I just took a t out of the t squared. Okay, now let's do one more step. So I got my t dt. Okay, this is why I multiplied it. Now I need a 2. And there's no, whenever you're dealing with constants, you can just force it. What do I mean by force it? Well, this is just equal to integral t squared, 1 plus t squared multiplied by a half multiplied by 2t dt. Okay, everyone follow me on that? So I needed 2t dt. I think I got a question or something. Yeah, exactly. So I did not write t to the third here. It was t to the third. I wrote t squared, and I multiplied by a t in front. Okay. If I multiply this t here, I'm gonna get t to the third. So it's back. But I multiplied the t in front here to show you guys how I'm getting close to here. This is where I want to get. Okay. So I can replace stuff. So that's why I forced this t outside, my first step. And then I need 2t dt. So I just did this thing. This is equal to 1. Okay. So I just did that thing. Any questions up to this point? Okay. Now I can finally do my replacement, all that I've worked to up to this point. So I'm just going to replace it here so you guys have everything on the same thing, on the same paper, but I will do the computation on the last side. So let's see. What do I have? I said 1 plus t squared is u. So replacing, this is u. Okay. If 1 plus t squared is u, what is t squared? U minus 1, right? Okay. Parentheses, if you didn't like that, u equals 1 plus t squared. So t squared is equal to u minus 1. Okay. In case you don't know where that comes from. But multiply by this. Now, multiplied by a half. Multiplied by, what do I have here? I have 2t dt, which was my du, multiplied by du. This is not a W, this is a U, by the way. Okay, everyone follow me on this. Made sense. Let me do it like this so you don't think it's anything. Okay, any questions on what I did? Because now through a magical substitution, you can probably tell that the problem is done, more or less. Why do I say it's done? Well, what do I have to compute? I have to compute, I'm just going to rewrite. I have to compute integral u minus 1 u multiplied by a half, du. This is what I have to compute. And this looks very solvable. Because first of all, constant jumps in front, so it's just a half integral u minus 1 over u du. What do I do now? I just split this thing, this numerator, okay? So this is just equal to a half integral of u over u minus 1 over u du, okay? And I did not need this parenthesis in case you were wondering, but okay. Now this is just equal to, I can split the integral again, kind of basic operations, and I have now I can need the parenthesis integral of u over u du minus integral 1 over u du. Okay. What do I have? What do I have here? I have a half integral of u over u is 1 du minus, let's do this again, minus integral of 1 u du. Okay, and we know all of these, right? This is just equal to a half integral of 1 u du is just u minus, what is the integral of 1 over u? It's just log of u, okay? Plus a constant. So this is my final answer. Almost. Remember where we started. We started at t to the third 1 plus t squared dt is equal to this. Again, same thing. When you're applying substitution in indefinite integrals, always replace in the end. Okay, so you get actually the correct answer that you're willing to have. Because at this point, remember, even by definition, what was my definition? My definition was if I take derivative of the right side, I got to get the left side. Impossible, 2 different variables. So I have to replace my u. So now replace u, who was 1 plus t squared. Okay, so I just replace everything and I'm done. It's just a half 1 plus t squared, literally just replacing, not even thinking about it. Done. Okay, just replace my u and I'm done. Any questions on what we did right now? Yeah. Let me see. This. Okay, I think I have one more example. Then I guess we're just gonna do definite, which is absolutely the same exact thing, just one simple change. But no questions here? Okay. The next one is what is it? It's yeah, I think it's like this. It's integral of e square root of x dx. Yeah. Now, how do you deal with this? Again, as bottom line, ugly exponent usually points towards the by parts, because as I probably bugged you, you cannot get rid of exponents, and integrating e to square root of anything is, I don't know how to do it. So it's really ugly. So that's where the idea of substitution comes into play. Okay. You just think of it. Can I actually compute this? If the answer is no, then you probably need the substitution somewhere in there. Okay. So that's why I'm just going to take again, u is equal to square root of x. I like exponentials when integrating. They're rather simple. E to the power of u is easy to integrate. E to the power of square root of x, not that easy. Okay. So u is equal to square root of x. Now, using the same exact thing, it's dx derivative of u has to be equal to my du. Okay. Dx derivative of square root of x is equal to du. Dx multiplied by derivative of square root of x is a half multiplied by 1 over square root of x du. Okay. Now, this is you look at this and you have, okay, I kind of understand or believe you that you got like a 2t in the previous example, right? We got you believe me, let's say that I somehow managed to get this t, then 2t to replace it with a u, okay? But what do we do in this case? This is the square root of x. I don't see any square root of x's here, so where do I get it? And you can't, but you can make the observation that square root of x is equal to u. Okay? So using this, I can just write dx multiplied by a half multiplied by 1 over u is equal to du. Okay? So dx is just equal to 2u du. Any questions? Basically just moved everything that was underneath on the other side. So now it looks pretty good. I have x, everything with x on one side, everything with u on the other side, and I just have to replace this dx with this u thing. Okay, so I'm ready to do by parts, to do substitution here. Okay, so again, what do I have? I have integral of e, instead of square root of x, I have u, and I replace dx with this multiplied by 2u du. Okay. And this might look familiar. We did several of these in the by parts, but I'll just do it so we solve it till the end. To basically show you that by parts substitution, there's There's no rule that says in a problem you only need to apply one. You might need to apply both. You might need to apply an integration by parts twice. Okay. Basically, just be free to combine them however you want. Okay, that's what I'm trying to tell them. Because at this point, I have to compute this 2 jumps in front. Okay, 2 jumps in front here. So I just have to compute 2 integral e to the power of u multiplied by u du. Now, I'm fairly confident we have computed this in the by parts. Fairly confident, but I guess I can just sketch it. Might be a good reminder as well. So when I have this, when I have to deal with this thing with exponential multiplied by a polynomial or whatever, standard procedure. You know, first part, let's use the same. First part was e to the power of u. Second part was u. And I told you, and I still think it's the best rule outside of like the homework, which Niels asked me about it, but I just didn't think of it. And I'll do a video explaining what I mean. So don't worry. First part, e to the power of u. I just compute the integral of this. Integral eu du is just e to the power of u plus a constant, okay? Again, I'm applying the by parts now, so relax. Okay, so I take this and I write my integral as integral eu prime, which exponential is going to give the same thing, but remember the by parts, multiplied by u du plus, now I add up the first part on derivative, so it's eu multiplied by the derivative of the second, u prime du is just equal to both of them, no integrals, everything clean. Okay, does this look somewhat familiar? Remind you of something? Okay, now, you know, just to keep it like we did, this we want to compute. This is done. How about this thing? Well, let's use this is question mark. So let's use a piece. Let's use another piece of paper. Again, I had to compute integral eu multiplied by u du plus integral eu multiplied by u prime, which is just 1 du. Okay, this is equal to e to the power of u multiplied by u. Okay, just replace my derivative in the previous formula. And now I have integral e of u multiplied by u du plus integral of eu is just the exponential, it doesn't change. Okay, so this is just eu plus a constant is equal to eu multiplied by u. So the integral I had to compute, it just move this to the other side. Okay. Any questions of what I did? Yeah. It does not go anywhere. I just didn't want to write it all the time. It's still, she's talking about the 2 here, and it's not going anywhere. Now I'm just going to replace what I just computed. I'm just going to replace this thing with what I just computed and multiply with the 2. So this 2 never went anywhere. I just didn't want to copy it through everything that I'm doing here. Okay. Great point. Okay, but let's backtrack a little bit and look at the bigger picture. Bigger picture was, I started with this ugly thing, okay? Had an exponential of square root of x, which I said really bad, cannot solve. I applied a substitution to it, okay? I just said u is equal to square root of x, and I applied substitution to it. And I got this thing over here, which is ugly, but I can compute. So I just took the 2 in front, and I ended up having to compute this thing, which is a standard application to by parts, okay? And now I just do the standard by parts to it, ... and I get this answer for it. So now I got to move all the way back. What was it? My integral e square root of x dx was equal to 2 multiplied by integral eu multiplied by u du. Okay, this is what I got after applying the substitution. And now I have finally computed this thing. Okay, so I just replace e square root of x dx is equal to 2 multiplied by e to the u multiplied by u minus eu minus a constant. Okay, and again, before I'm done, replace u is equal to square root of x. So just replace everything. It's just equal to 2 e square root of x. I'm just replacing right now. So, and my answer is done. Okay. Any questions of what I did right now? I think in terms of logic, this simple problem is probably the hardest you're going to face in this course, in the sense that you had to apply a substitution and a by parts to it. So if you could follow the main logic of it, I think you're in a good spot. Now, realistically, probably in the problems or whatever, you're going to have uglier functions or uglier numbers. But as long as you get the logic and you can follow the logic, the computation will come if you just take it slowly, step by step. Okay. I thought it's more important for me to show you basically the logic of what you're doing rather than just put like a page-long formula here and lose you through the computation, which again will come, and it's only based on exercise, the computation itself. Yeah, I think this, I'll just end it rather here because I don't want to start the definite right now. So let's just have like a 10-15 minute break now, and we're gonna continue afterwards. Here you go. Thanks. Very nice. Okay, let's get back to it. So now we're going to do substitution applied to definite integrals. And as you can probably guess by now, it's really not much of any difference, really. It's just, okay, so remember, we know how to apply something, or we kind of learned how to apply f of x dx, something like this, okay? But now the question is, how do we do if we have a, b, f of x dx? And the only difference that's gonna pop, remember we wrote like that kind of two-rule thing, how to apply this substitution. The only thing that's gonna happen is now you're gonna replace b is gonna become u of b, and a is gonna become u of a. All right, that's literally the only thing that's gonna change. Okay. And another thing, but I'll tell you once we get there. But that's the only thing you gotta keep in mind. So let's do a simple example. Let's do integral of 1 x log of x dx from, let me see, from let's do from e to e squared. Okay, e is just a number. E is 2.71. If you don't like it, but okay, doesn't matter. Cool. Now, again, you look at this, don't really know how to get it. Someone might argue you can solve it by parts. You can, but we're in the substitution case, we're going to solve it by substitution. Okay, so again, prime candidate for doing substitution is log of x. So I'm just going to say u is equal to log of x. Okay, prime substitution. Now, dx multiplied by u prime is equal to du. And solving it, dx multiplied by log of x prime is equal to du. Dx multiplied by 1 over x is equal to du. And the other thing that changes is instead of e squared, so I'm just going to write instead of e squared, what am I going to write? I'm going to write log of e squared. Okay, which is just 2 by definition. Okay, log of e squared is just 2. And instead of e, I'm going to write log of e, okay, which is 1. Obviously, if here I had 1 million, instead of 1 million, I would just write the log of 1 million. Okay, makes sense? So if I'm replacing, the idea is that if I'm replacing this log of x with u, and I'm basically now integrating over a new variable, I have to adapt my margins of integration as well. Okay. Like, for example, if I just use the notation u is equal to x plus 1, I would just integrate from e plus 1 to e squared plus 1. Okay. Does it make sense? You just have to adapt the margins of integration as well. Now, so this is equal to integral, and again, here instead of e, I have log of e. 1, instead of e squared, log of e squared. 2, and I have 1 x u, log of x is u from here, multiplied by dx. Is this a good way of writing the integral? No, really bad. I have x and u and dx, really bad, okay? But what do I see here? And again, this thing, what I'm writing here, I would highly advise, at least until you're more proficient or whatever, to do it in your notes, okay, in your computation. Write all the intermediate steps, take it slow, it's perfectly fine. When you write on the paper, okay, when you write on the exam or whatever, this thing doesn't really make sense, okay? And I personally, as a grader, I don't really need to see this, okay? But in your notebook, in your computation and whatever, perfectly fine to write it out. But okay, now I have integral from 1 to 2 of 1 over u multiplied by 1 over x dx. Okay, just split this into 2. Why did I split it? Well, look here. Dx multiplied by 1 over x is equal to du. I have 1 over x multiplied by dx. This is just equal to integral 1 over u du. Okay, and this is now a good integral. Make sense? So when you apply substitution, definitely I would highly advise you to write this part, the left side. Basically, show me, write this thing. This, right. You're showing me why you're replacing, you're showing me how you're replacing it, and you're showing me that you understand what you're doing, okay? And it helps you follow your train of thought. Once you've done this, you can just give me the answer. You can just give me the answer to this. Perfectly fine. I believe you. Make sense? Okay. So I got integral of e squared 1 over x log of x dx. Okay, and I got it's equal to integral from 1 to 2 u du, which we know that the primitive of this of 1 over u is just log of u from 1 to 2. Now, question. Okay, after all of you are writing, do I have to replace my u again? Do I have to replace u equals log of x dot whatever? And the answer in this case is no, because this thing is a number, okay? Remember, previously in the indefinite, you had apple and oranges, you had x and u. In this case, I have just numbers, okay? This log of u gives me a number. Okay, if I compute this gives me, plugging in, log of 2 minus log of 1. So there's technically nothing to replace, okay? This is a number. So in indefinite integrals, always replace your substitution in the end, okay? Indefinite, so I can just write it. In indefinite integrals, replace substitution in the end. In definite integrals, no need to replace. Because you get a number. Okay, this is a number. So there's nothing to replace in this case. Okay. Let's do another example of definite. Okay. I think it might be useful. Let's do another example. And then I'll show you something with a really, really fancy name, but intuitively simple. So I'll show you right now. Let's take another example. I think let's just take an example of what we solved, because genuinely I can't think of anything that's outrageously different. They're all kind of the same thing, to be honest. Even in your book, I checked. They're all really extremely similar. So this is actually one from your book, but I mean, we solved it after another form. So it's x square root of 1 plus x dx. You probably remember this one. Let's do an x. Yeah, let's keep it like that. It was x squared. Okay. Let's do it from 0 to 1. Okay. Again, the only change that's going to happen from how we solved it. This was the first one we solved, right? Yeah. The only thing that's going to change from what we solved initially is the fact that we're going to change the limits of integration. We're going to change 0 and 1. Okay. That's the only thing that's going to happen. The only difference. Otherwise, it's literally solving the same exact way. That's why I'm just going to go a little bit faster, because the only thing that's going to change is only the limits of integration. Okay, literally that's the only thing I'm changing here. So remember, what did I do? I said u is equal to 1 plus x. I'm just replacing what's inside, what's underneath the square root. Okay. Again, dx multiplied by u prime. I don't think you need to write it, because it's basically the same thing as I did initially. So I think it would be more beneficial to follow me, but your choice completely. Okay. This is just equal to du. Again, this is just dx multiplied by 1 plus x. Everything derivative is equal to du, which is dx multiplied by 1 is equal to du. And this is different. Okay. This is different now. Different from indefinite. Instead of 0, what are you going to get? Okay. If x is 0, instead of x equals 0, what do you get? You get, when I replace 1 plus 0, you get 1. Okay. And instead of x equals 1, you get 1 plus 1 is equal to 2. I know. Amazing math. Anyway, that's the only thing, is your limits of integration change. Okay. That's the only thing that changes here. So this is just equal to exactly what I wrote previously. I could even copy myself. But integral, again, my limits of integration change. 1, 2. And again, it's the same exact thing. It's u minus 1, because x, instead of x, if u is equal to 1 plus x, then x is just equal to u minus 1. So x is u minus 1 multiplied by square root of u du. Okay. Same exact thing, but my limits of integration changed. Okay. And now we're going to solve it the exact same way, just that I'm not going to replace it. I'm just going to plug 1 and 2 and be done with this problem. Okay. So again, exactly the same way you solved the indefinite, you solved this one. You just split this, u square root of u du plus 1, 2 square root of u du. Again, I'm just writing from my notes up to this point, literally just writing from my notes. And now I apply the formula and I get 1 3/2 plus 1 u of 3/2 plus 1 between 1 and 2. Oh, this is a minus. Apologies. This is a minus. It's this minus over here. Sorry about this. This minus over here. Okay. Minus. Let me draw this. This is the thing you need to write always. This always right when you're applying by parts. Okay. And it's minus, what do I have? 1/2 plus 1 u a half plus 1 between 1 and 2. And again, remember, in the indefinite case, what we did is, okay, I told you we got to these functions. Oh, did I get? Sorry about it. Yeah, no, it's negative. Yeah, I added this negative there. If you're talking about this minus, yes, it's minus. But yeah, so I got these two things. I remember in the indefinite case, I told you, okay, now replace your substitution back and give me the answer next, and you're done. In this case, just plug in the numbers and you're done. Okay, plug in, instead of u, plug in 1, 2, and you're done. Okay. So if you want me to give the answer relatively nice, I just have integral 0 to 1 x square root of 1 plus x dx is equal to 1 3/2 plus 1 plus 1. Again, I'm just copying what I got there, minus 1, 2. And again, now we just plug in the numbers. The answer is 0x1 plus x dx is just equal to 1 3/2 plus 1. And again, 2 to the power of 3, 2 plus 1 minus 1 to that power. I'm literally just plugging in. Okay, nothing special. And this is a number, and you plug in your calculator because you are allowed a calculator, and you got the final answer, and you're done. Okay? Plug in, calculator. Dot. Okay. So, as I said, the only thing I wanted to show you here is that the only difference when you're applying substitution to substitution in a definite compared to an indefinite is the fact that you got to change your limits, your margins of integration, basically the numbers next to the integral, they change as well, obviously. And the fact that in the end, you don't need to plug in u equals x, etc. Again, you just solve that. You just solve that to a number and you're done. Okay? Any questions on this? On anything regarding substitution? Okay. I'm gonna assume nobody understood anything, but let's move on to the next part. This is not a personal favorite of mine, but I see it in your book, and Neil said I should go over it. So here I go. Okay, it's called Polynomial Division. Okay. And no, it's not going to be hard. Polynomial division. Ugly term for something that's not as ugly as you might think. What's the idea of this? Okay, you have to compute integral of a polynomial of x over another polynomial of x dx. Okay, what does a polynomial mean? It just means it has x to some powers there. Okay, and let's take an example. Let's suppose I need to compute integral of, and I'm literally gonna use the book. Why not? X to the 4th plus 3x squared minus 4 over x squared plus 2x dx. Okay, and the whole idea is you have no idea how to solve it looking at it as it is now. So the idea is to apply polynomial division. What does polynomial division mean? It means, in uncommon terms, splitting the thing up top, splitting the numerator, so that eventually it has a power smaller than what's below. Okay? fancy term for that. What do I mean? Okay, so here's what I mean. Let me see. The idea is that I can just x to the fourth. I have here x to the fourth, and here I have x to the square. Okay, drop the integral. You don't need the integral for this because you're gonna, this happens in your notebook, in your head, or even on the exam, you can definitely write this. So I'm just gonna say that x to the power of 2 plus 2x multiplied by x squared, okay? Which is usually I multiply with what is the biggest power up top, okay? Just so I get the biggest power. In my case, it's x to the fourth. I have an x squared here, so I multiply with an x squared, okay? Just so I get the x fourth, the biggest power up top. So in this, I get x to the fourth plus 3 x to the third. Okay, everyone. Yeah. I don't know where that 3 comes up, but it's a 2. Okay, no rocket science happening here. Okay, now move back one step. I am polynomial divisioning whatever, etc. This thing, x to the fourth plus 3x squared minus 4. This is what I'm polynomial divisioning. Okay, don't quote me on that. That is not a term. Okay, but regardless, the idea is to get rid of the bigger powers. So how do I get rid of the bigger powers? And write everything in terms of like x squared plus 2x. In this case, do you agree with this way of writing? X to the fourth plus 2x to the third minus 2x to the third plus, and I copy 3x squared minus 4. Okay, what changed here? I just added this and subtracted this. So this is 0. Do you agree with what I just did? Okay. I just added this thing and then I got rid of it. Okay. Somewhat of a not okay. Okay. Again, I want to get rid of the bigger exponents. So I'm trying to create this, which is what I got. I'm trying to create that. If you look at my equation, there's no x to the third. There is no x to the third there. So what do? Is I added 2x to the third, and then I subtracted 2x to the third. Okay? This together gives me 0. Wait, I add them and I subtract them because if I do this, I can write, instead of this thing, I can just write x squared plus 2x multiplied by x squared. That is the only reason I did what I just did. Okay? And it's minus 2x to the third plus 3x squared minus 4. The rest I just copy. And now you're going to ask me, why would you do such a thing? First thing, notice the power here, I got x to the third. It's a smaller power. Usually when you're integrating smaller powers means you're doing something good. Okay? Rule of thumb. Also, if I go back to my integral, I have x to the fourth plus 3x to the square minus 4, x squared plus 2x dx. Right? This is what I had. And now I just replace with what I got here. And I get integral x squared plus 2x multiplied by x squared minus 2x to the third, 3x squared minus 4. X to the second, 2x dx. Okay, I just replaced. Nothing else. But what do I notice now? I notice that if I split this, okay, let's do this. So you put an equal. I just want to move on another page. This is just equal to integral of, and I can split it, x power of 2 plus 2x, x squared over x squared plus 2x minus, no, okay, let's do plus minus 2x to the third, 3x squared minus 4, x squared plus 2x dx. Okay, what happened here? This was my thing, this was my equation, so I just split it. I just split it into two fractions. Okay? I split that whole thing into two fractions. Why did I do that? Well, now I can simplify this with this. Okay? That is the only reason I did that. Now hopefully it kind of starts to make sense why I'm doing what I'm doing, because now I can just write this as integral of x squared dx, which is trivial, plus integral of minus 2x to the third, 3x squared minus 4, x squared plus 2x dx. Okay? Why is this better? Integral of x squared plus x squared dx, we know it. Okay? We've done it several times. And this is an integral of a fraction, but it has a small power. This is a 3. Before I had a 4. As I said, small powers means you're kind of doing something right. Okay? And now I'm going to do exactly what I did for that x to the fourth to the x to the third, and so on and so on and so on, until up top I have something that's small and I can't do it anymore. And this is what they call polynomial division. Obviously now I guess you can come out with more complicated rules, or I can just tell you that you can see it, how it's simplified, there you can how it's simplified, but this is the underlying logic. And it's perfectly fine to do it step by step, or if you're just really comfortable, you can just blow me out of the wind and tell me if I do polynomial division, I'm gonna get this, okay? But this is how you should think, and it is just a matter of how fast you can do it, I guess. Okay, but any questions on what I did right now? Any questions specifically on what I did? Because what I did up to this point, I'm gonna do again, and this is what I'm gonna call polynomial division. Okay. Okay, I'll just explain what I did here first time. Okay, so I noticed the fraction, and whenever you have a fraction and a fraction of two polynomials, which is a fraction of powers of x, no exponentials, no nothing, just powers of x, okay, added and subtracted and whatever. And you notice that the fraction up top has a bigger power than the fraction below. You should consider that a polynomial division thing might be a good way to start. Okay, might be a good idea to try. You might solve it without. I have no idea, but it's worth trying. So how does my whole idea start? I want to get the biggest power out, which is my x to the fourth. Okay, my biggest power is x to the fourth. My biggest power down below is an x squared. So I just multiply by the difference between them, which is x to the power of 2, which is 4 minus 2, if you want it. Okay, I just multiply by it, and I get this thing. Now I turn back to my exponent, and I notice that, okay, I got this thing, x to the fourth plus 2x third, whatever, but I can't apply it here. So the trick is to force apply, okay? You just add and subtract the extra term. So I had no 2x third, so I just added a 2x third so I can apply my thing. And then I subtracted a 2x to the third. And then the rest I just copy. Okay? And after this, you can replace immediately, or you can just do the whole computation there. However you're comfortable. I just replaced you so I don't lose more of your interest than I got and show you that it gets better, right? In the sense that I get x squared here, and now I don't have an x to the fourth. I only have an x to the third. So it technically gets better. Okay. Now I have a fraction, and it's the same exact thing. Again. Okay, let's try and I don't think there's any rule in any book or anything about how to do this polynomial division. So I'm just gonna do one right now. First of all, check if higher exponent up top versus below. Okay, so what do I mean by this? If you have a fraction, check if the power up top is bigger than the power below. Okay, in my case, I have a 3 up top and a 2 down below. So I can technically do something to this. Okay, now multiply by the quotient. Okay, by quotient of biggest over smallest. Okay, what do I mean by this? Is I mean that in our case we multiplied. Remember, we multiplied and I'll quote the previous example. I had x second plus 2x. Okay, this is the smallest. The biggest is x to the fourth. So I just multiplied by the biggest over the smallest thing. Okay. I just multiplied by this x squared. Okay. Multiply equal quantity biggest to smallest. And then force the group up. And what do I mean by force the group up? Force the group up, add, subtract. Okay, this is what I mean, force the group up. Force the group up. And done. Okay. So if you didn't get it on the first thing, no worries. I'm literally gonna do the exact same thing 2 more times, so you're not losing anything. Literally the same exact thing, just instead of x to the fourth, I'm going to have x to the third. So check if higher exponent up top versus below. Again, I have x to the third, x to the 2, so I can apply it. Now what do? I multiply. Let's do the denominator. Okay, multiply the denominator, which is x squared plus 2x by the quotient of biggest to smallest. Okay, what is my biggest here? My biggest exponent is this. Okay, so minus 2x to the third. What is my smallest? It's x squared over x squared. Make sense? What I'm doing right now? Okay. Multiply this, and I get this goes away, and this just becomes an x. So this is x squared plus 2x multiplied by minus 2x, which is just minus 2x to the third minus 4x squared. Okay. And now force the group up. Force the group up, right? So I had my thing up top is minus 2x to the third plus 3x squared minus 4. Okay. And this is equal to, and I said, force the group up. So what does it mean to force the group up? I copy this. So I copy it, minus 2x to the third minus 4x squared. Now, I just add 4x squared here, and I copy the rest. Now, one observation. You're gonna tell me, hey, you kind of had an x squared before, okay? Can't you just take it from there and etc.? Okay, okay. Here I have 2 minus 2x to the third minus 4x squared, okay? And here I have minus 2x to the third plus 3x squared. And could I technically take from this or whatever, from this x squared? Yes, but do not. It becomes more complicated to keep track of the powers and the numbers. This is by far the easiest way. Copy it. Copy what you just had. Okay, copy what you got. So I copied it right here. Add back the term, and then copy the rest. Okay. So again, this is 0. That is 0, and you can see that I have the same thing left and right. Again, why is it good that I did? Well, I can group up stuff and I group this thing up. I know this is equal to x squared plus 2x multiplied by minus 2x plus 4x squared plus 3x squared minus 4. Everyone follow me on that. Okay, now again, okay, disclaimer, you don't need to go in and plug into the integral every time you're doing this. Okay, you can just do it once at the end and do the computation here, however you like. I'll just plug it in right now so you guys are convinced that we're doing something right. Okay, so our equation was this, and my claim is that now this is equal to x squared dx. Again, the thing from the start does not change, plus, so it was this, which didn't change, plus now this integral. Okay, and I'm writing this integral as minus 2x to the third minus 4x squared plus 4x squared. Again, I'm just rewriting the transformations. Fancy term for what I just did. Okay, x squared plus 2x dx. And again, just like before, I decided to split it here. I split it like this. So I get integral of x squared dx plus integral of minus 2x to the third minus 4x squared x squared plus 2x dx plus integral of 4x squared plus 3x squared minus 4 x squared plus 2x dx. Cool. Now, why did I do this? Well, this is x squared dx. Again, I'm just carrying it for the sake of doing stuff correctly. But here you just get this is just x squared plus 2x minus 2x. Oh, sorry, it's 2x dx plus integral 7x squared minus 4 x squared plus 2x dx. Everyone agree with what I just did here? Okay, so now I have x squared dx plus, this goes away again, and I have integral minus 2x dx plus, look at this fraction. It looks almost beautiful. Okay, so again, power is decreasing now. I have an x squared left. It means I'm doing something right. And surprise, surprise, I'm going to do the exact same thing one more time. And after that, the integral is kind of done. Okay. So I check all my steps. Is the thing up top bigger? Bigger or equal? Okay, bigger or equal. And it is. So now I just multiply my smallest, x squared plus 2x. I multiply it with 7x squared over x squared, which is 7x squared, which is my biggest, over my smallest. Okay, and I get x squared plus 2x multiplied by 7 is equal to 7x squared plus 14x. Okay. Now, second step or third step, or no, this is the first step, whatever. You probably got it. I just force this 14x because you see I have no 14x. So I just force it out. Perfectly normal. 7x squared minus 4 is just 7x squared minus plus 14x minus 14x plus 4. Okay, this is again 0, so I have not changed the equation. It would be minus 4, yes. It's the minus, as I said. This thing does not change, so it's a correct. It's a minus 4. Yep. Yeah. It's a minus 4. But yeah, so now I return to my equation again. This thing can go on your computation paper. It can go in your head. I don't really care where it goes. Okay. If it helps you to write on a paper, write on a paper. But what I'm saying is it's not necessary. Okay, this is not necessary. I'm just writing all the steps so you guys know what I'm doing. So now this is just equal to integral of x squared dx. You know, just continuing my train of thought. This was like in my head or whatever, or on the paper. Again, it's not bad to write it. You can write it. You're perfectly fine to write it on the exam paper, no problem. Actually shows the grader that you've done work. So I have no things, but yeah, I'm just continuing this. Integral minus 2x dx plus, again, I do the exact same trick. 7x squared plus 14x minus 14x minus 4, that's a minus, yes. X squared plus 2x dx. Again, same thing. I split it here and I get integral x squared dx plus integral of minus 2x dx plus integral 7x squared plus 14x x squared plus 2x dx plus integral minus 14x minus 4 x squared plus 2x dx. Okay, and again, this is 7. This integral is just 7 because that's the way we create it. But I'll write the intermediate step right now. So, okay, plus integral 7x squared plus 2x x squared plus 2x dx plus minus 14x minus 4 x squared plus 2x dx. Okay, this goes away. So what do I have? I have integral of x squared dx plus integral of minus 2x dx plus integral of 7 dx plus integral minus 14x minus 4 x squared plus 2x. Okay, dx. And now all that's called polynomial division is done. Okay, everything with polynomial division is done, and we're only left with solving this. You're gonna say, Okay, yeah, but these three things are trivial, right? We know how to compute that. Now we're stuck with this fraction. And the rule or the reason you tend to do this polynomial whatever is because if you have a fraction where the power below is bigger than the power above, it usually helps to think about log of what's below. Okay. And it's not a standard procedure. I mean, in my case, I think it's pretty standard. And I think in this class, there are no examples where you're not going to get that thing. Or you can just do the substitution, or you can just do, I don't know, there are multiple, there are all sorts of possibilities you can solve this. But regardless, we're not here to teach, we're not here to solve this. I'm fairly confident you should be able to solve it. I think everything can apply. What was important is you get the this polynomial division, okay? So any questions on the polynomial division alone? And how do we got it, okay? Yep.
Yeah, so if you don't want to do the whole thing on your exam, what would be sufficient to write in order to show your line of thought?
Great question. If you show me, so if you just write to me, where was the example? If you just write x to the fourth plus 3x squared minus 4 is equal to x squared minus 2x plus 7 multiplied by x squared plus 2x minus 14x minus 4. If you just show me this, which is, if you just say this, okay, which is, it's this x squared minus 2x plus 7 is basically this, which is just I'm still like an English word right now. Which is basically what you get after dividing, and then this is the remainder of the division. If you just write me something like this, then you're done. Okay. Because okay, if you're not convinced why what I just wrote is the same as the thing up top, let's just replace. Okay, so integral of x4 plus 3x squared plus 4 over x squared plus 2x dx. Okay, if you just apply this formula over here, okay, and I just replace it, integral of x squared minus 2x plus 7, x squared plus 2x minus 14x minus 4, x squared plus 2x dx. Again, I just split it, and I get integral of x squared minus 2x plus 7, x squared plus 2x over x squared plus 2x dx plus integral minus 14x minus 4 2x dx. Okay, and now this goes away, and what are you left with? It's basically the same exact thing as up top. You guys convinced now that it's the same thing as up top? Okay. Because this goes away and this is just splitting the integral over this. But so it's the same thing. But I'm struggling for the English word necessarily, but what is left outside the parentheses is called the remainder of the division. Okay, this is what it's left, just like dividing two numbers. Okay, so this is the remainder, and this is the result of the division. I'm liking the word right now. Like, so for example, if you divide 7 by 3 and you get 2 remainder 1, what is this thing called? the result of the division. I'm liking the word right now. Whatever. You know, just think of this thing that remains here as the 2 from this division, and the fraction here as the remainder 1. Okay. So you're basically dividing this big polynomial to this smaller one, and you're gonna get a remainder, which is this, and the result of your division, which I'm liking the word. Yeah. No, you are supposed to do. You're going to solve this, but again, I think there are multitudes of ways in which you can solve the last one, and I just wanted to make sure that you got the computation of getting there. Okay. So yeah, I guess time's up. So that's kind of it for today. But yeah, see you guys tomorrow.